First, thanks for inviting me to speak on this panel. I also prepared a couple of slides. One correction is that I would say that my journey in quantum computing is relatively short, but we certainly has done a lot more in the classical computing, especially on customization side. Let me show you. So just to answer your question, what are the opportunities there, right, for customization for quantum computing? So in the classical world, we get a fantastic result when we do customization. For example, this is on genome sequencing. If we use customized acceleration engines, we get 28x speed up. If you look at some of this real-time signal processing using our LSTM, you see over 200 x energy efficiency, because this is edge computing. We care about energy efficiency more than the performance alone. You do data compression, you see close to 40x speed up with a customized accelerator. And using systolic array for some of this deep learning application, we see 7x. These are actually just all on FPGAs. In fact, if you specialize it to ASICs, you will see even more. So the natural question is that, hey, what's the opportunity if we can specialize the quantum architecture? Right now, we have a relatively fewer qubits to play with, but once that number increases, so what are the opportunities to specialize? First, actually, Yufei is a co-organizer of the workshop. I want to highlight one of her work. In my opinion, is probably one of the first to look into this direction, to look at some application-specific yield optimization, where you want to increase the success rate at the fabrication time for the fixed frequency superconducting qubit designs. So they have a relatively simple algorithm to do iterative optimization to decide qubit connection and allocation. There's a very impressive result on yield enhancement. But it didn't say very much about the circuit fidelity when you run the application, right? So this is where we come in that to look at the possibility of changing the connectivity with the goal of optimizing the fidelity. Give you this very simple circuit on the left-hand side. And this is one of the early IBM architecture on the right-hand side with only 5 qubits. You can prove actually mathematically that you have to insert one swap gate no matter what. How do you arrange the qubit mapping or the scheduling? However, if you change the architecture a little bit, you say, hey, I changed that vertical connection to the horizontal connection, same number of couplings, and then you can actually get a solution with no swap gate, right? So now this is actually motivate now to do the research, saying maybe with the existing architecture, we can do some modification, either augmenting an edge or removing an edge. And let's see that how much specialization can we achieve. So we actually look at the 2 architectures. One is the heavy hexagon that basically is inspired by the IBM architecture. The other one is grid-based architecture inspired by Google Sycamore. We're only looking, in this study, we're only looking at the superconducting qubits architecture. So these are represented the possible edges you can insert, but you are not going to add all of them because there's various kind of physical limitations. The challenge to do this study is that you cannot just try to insert every one to see which one is the best. You get a huge possible number of combinations. The solution space is way too large. There's also some, for example, combinations you may disallow. You says you cannot have 2 edges that crosses, right, in this architecture. And so how do you do the exploration? In fact, we have a very recent paper coming out in this special issue on the emerging technology and circuit systems in collaboration with Murphy New at Google Quantum. So what we can do is the following, that actually there's remember that Anisha also mentioned, we have a very efficient layout synthesis tools based on SMT formulation, where you basically lay out what are the variables that are basically space-time mapping and what are the constraints. It turned out we can encode one more constraints. Basically, you say each edge that there are some of these possible places you can add a new edge. You can represent it by a variable. It can be either 0 or 1. And if it's 1, you will add this edge. If it's 0, you will not add this edge. And the total number of edges we want to add is bounded by some small constant. Let's say I want to add no more than 2 edges. And then you can also add some constraint to model the conflicts, right? So this represented the trade-off between the flexibility and also the fidelity versus fabrication cost, and also the crosstalk potential. So here are some results. It's quite interesting. It's not quite in the the 10x, 40x range we see on the classical computing world, but it's nevertheless it's encouraging. And we have this one, the first curve on heavy hexagon, because it's a much sparser architecture. Adding some edges can give you a big boost on the fidelity because you can cut down the swap gates quite a bit. The other one is the grid architecture, which already has relatively high connectivity. So adding more edges is a limited gain. Let me just show you one result. For example, this is the default architecture, like a Google Sycamore. And if you start with the IBM hexagon architecture, just adding 2 edges, right, that you can be already comparable to Sycamore. And then if you add 3 edges, you are ahead, or 4 edges, you are ahead. But if you look at the average connectivity, it's still 2.2 or 2.4, much lower than the grid-based architecture with 3. So this kind of a study is very useful to tell you the potential if you do some special customization, that what's the best you can achieve. This is all using the QAOA as the motivational examples to have. And the moving forward, that's just I think there's a lot to gain working with the domain experts in the technology physics domain. Misha mentioned this paper where was coming out next week at SCCAT, where actually we see a lot of potential to work on this programmable architecture, where you can really adapt that quickly to the application we have at the hand. So I think there's a lot to be gained, to be learned in this area. We'll continue the exploration. So with that, I will end here and be happy to have some more discussions.